And welcome to this extra couple of video examples here from Math 237. We're going to look at a couple of double integral type questions. The first one asking us to evaluate the following double integral here over that region dxy, which is in the first quadrant of the xy plane, bounded by the following curves: x times y equals 1, x times y equals 3, x squared minus y squared equals 1, and x squared minus y squared equals 4. So as always, a good way to start is with a sketch of the region. So as part of our solution, we'll draw the region in the xy plane. Notice it's in the first quadrant. So I'm going to put this up in the corner so we can see that as we work out our solution. Alrighty, and so notice that x times y equals 1, of course, is the same as y equals 1 over x. X won't be 0 anyway. And so that's just a part of a hyperbola, and the same with y equals 3 over x. That one would just be stretched vertically by a factor of 3. So we can start with drawing those ones. So here's our 1 over x looks something like that. And 3 over x, of course, stretched vertically, something like that. All right, so we'll just label these. So y equals 3 over x, y equals 1 over x. Alrighty, and what else do we have here? We've got these hyperbolas. X squared minus y squared equals 1, and that, of course, is the hyperbola with your asymptote of y equals x. All right, and so we think about that one. And the x-intercept is x equals plus or minus 1, but we're in the first quadrant, so x equals 1, and there are no y-intercepts. All right, so if x equals 1, let's just put that somewhere on the sketch. Actually, that would have to correspond to the intersection of this asymptote with that curve. But that's not important right now. Anyway, the asymptote there along y equals x, so that approaches like that. Okay, so that was the curve x squared minus y squared equals 1. And x squared minus y squared is 4 is similar, except, of course, your x-intercept will be x equals 2. So it'll look like that. So what we're looking at is the region bounded by those 4 curves, which obviously is this part right here. All right, so again, that curve. Oh, wait, we've already labeled that curve. Sorry. That curve there, x squared minus y squared equals 1. And this curve right here, x squared minus y squared equals 4. All right, so we have all of our curves labeled up here. And you might think, okay, well, let's try to describe this region with inequalities. Well, if you think about drawing either vertical or horizontal rectangles in here, it's not going to be very easy to describe with inequalities. Even if you solve that for y as a function of x, it would involve a square root function. And if you think about it, you'd actually have to break up the region into probably 2 or 3, probably 3 pieces in order to get an idea, in order to describe that nicely with inequality. So that would be a lot of work. So what do you think would be a good way to do this one? Anyone? I'm not hearing anything. Why don't I just tell you what we should do? Mapping. So we're going to map to a nice region. And so remember the work we did on inventing mappings. The idea was to think of the 4 boundary curves in terms of something equals a constant, because that would be really, really nice. If we could let that something be u or v, that could map into a rectangle where u is equal to a constant or v equals a constant. Or even something simple would be good, but a constant would be ideal. And in this case, remember this curve here, y equals 1 over x, we were sort of given a hint in the question that it was written as x times y equals 1. So if we write that as x times y equals 1, this curve becomes u equals 1 if u equals xy. And that curve there is x times y equals 3. So then u equals 3 in the UV plane. So that's what we're going to do. We're going to let u equal xy. All right. And can you guess what v should be? X squared minus y squared, right? Because then that boundary curve would map to v equals 1, and that curve there would map to v equals 4. So v equals x squared minus y squared. And so what happens then is our region will map to the rectangle where u equals either 1 or, sorry, from that one, u equals 1 or u equals 3. So let's draw this in the UV plane. So if we have u equals 1 and u equals 3, those boundary curves mapped to those lines. Now, of course, we don't really need to think about mapping the entire curve, but I'm just going to map the entire curve because we'll see where they intersect in the UV plane. But to be really proper, you should probably just consider the interval over which they're part of the boundary of this, but that would be tedious. So let's do the whole curve. And then the other ones, x squared minus y squared equals 1 gives you v equals 1, and x squared minus y squared equals 4, of course, maps to v equals 4. So that one goes from 1. So one of the boundary curves is 1, and the other boundary curve is at 4. And you can see that's bounded here. If you want to make sure that the mapping maps the inside of this region to the inside of that region, you could plug in a point to make sure of that. That usually it doesn't turn things inside out unless there's some kind of a reciprocal going on or something like an inversion map or something. But anyway, if you wanted, you could plug in, say, x equals 1.5 and then figure out an appropriate y value that's in there and make sure that maps to somewhere inside here if you want. So, but anyway, this is our region in the UV plane. So we can clearly see that u is between 1 and 3, and v is between 1 and 4. All right. We also know about the Jacobian. We can calculate the Jacobian of this map to prepare for the change of variable theorem. Okay, so we want well, for now, let's calculate di uv by di xy. Okay, and that'll be the determinant of the derivative matrix of this mapping. So remember the mapping here was u equals xy and v equals x squared minus y squared, right? And so for the first function, the partial derivative of that would be y and x respectively. And for the second function, di v di x is 2x, di v di y is minus 2y. And so we work out the determinant of this to be negative 2y squared minus 2x squared, which is, of course, negative 2 times x squared plus y squared. All right, and we should ask ourselves, is this ever equal to 0? On our region. If you recall the region that I drew earlier, it's not going to touch the origin, so this thing certainly is non-zero on dxy. Okay, so that suggests that there's an inverse mapping on dxy, although the inverse mapping theorem only really tells us that there exists an inverse mapping in a neighborhood of each point on dxy, but we often just make the jump that, okay, you know, it's going to be invertible on this. All right, so the next thing we're going to do is use the change of variable theorem to work out the double integral that we wanted to do. Okay, so remember that the bounds in our UV plane are between 1 and 3 and between 1 and 4 for u and v. So by the change of variable theorem, okay, the double integral over dxy of, and the function we were trying to integrate was x squared plus y squared dA. Okay, that's going to be the double integral over my UV region, duv, which was this set, by the way, it's going to be the same function. We want to evaluate the x's and the y's in terms of u's and v's, but if you look at the mapping we had, it's not so simple. It's not obvious to solve for x and y in terms of u and v. So let's just hope that the problem will go away. X squared plus y squared times, and then what happens to my dA, or if you want to call it the dx dy, that's going to be, by the change of variable theorem, the absolute value of the Jacobian, and then du dv. And I always remember it as I want the sort of the du dv's to sort of cancel and to leave a dx dy, because that's what it was. So the Jacobian we need here is di xy, okay, by di uv. Okay, so in fact we calculated basically the Jacobian of the inverse of the map that we want the Jacobian for. So, but we could use the inverse property. So let me just backtrack for a second to the Jacobian calculation. So by the inverse property, okay, di xy by di uv, if we think of again the inverse map from u and v to x and y, that's just the reciprocal of the Jacobian of the original map. Okay, so that'll just be negative 1 over 2 times x squared plus y squared. Alrighty, and so there's the Jacobian we want to put into this absolute value, so we drop the minus sign. And remember that our bounds are from 1 to 3 and from 1 to 4, so we'll need that in just a second. So this will be the double integral for u between 1 and 3 and for v between 1 and 4. That's just a sort of a non-standard maybe notation there, of the function x squared plus y squared, which we have to put in terms of u and v in principle, multiplied by the absolute value of the Jacobian, which now becomes just 1 over 2 times x squared plus y squared du dv. And by golly, would you look at that. The x squared plus y squareds cancel out. There's a bit of a goodwill hunting moment there. High five. And there we go. They cancel out. And so you just get the constant factor of 1/2 that we can take out. So it becomes a very easy integral. You get 1/2 integral. U goes from 1 to 3. V goes from 1 to 4. Okay, so that's dv, du. Okay, and you could work that out with not too much trouble at all. V goes from 1 to 4, so the antiderivative is v, subtract them, that's 3. Okay, so 3, take that out, that'd be a 3/2, and then integrate from 1 to 3, du is just times another 2, which cancels out the 2. Okay, and so you should just get 3. And that's what I got there too. Now, there is actually a much easier way to work out this double integral, even though, so at the point where we had here, once we took out the factor of 1/2, you could recognize that easily as the volume of the rectangle that we had in the UV plane, right? So the rectangle has width of 3 minus 1, which is 2, and a height of 4 minus 1, which is 3. So 2 times 3 is 6. That's the volume of the rectangle, and times 1/2 is 3. So you don't always have to, work out the integrals. You could use a geometric interpretation, especially, again, if your integrand is a constant, which you could pull out. Well, that's the end of the first example, and let's take a break. And we're back. Let's look at another example. Okay, the second one is a famous integral. And you might wonder how this is connected to double integrals. But the question is, evaluate the integral, the improper integral from 0 to infinity of e to the minus x squared dx. Okay, so this ends up being, a really important one for statistics and actually lots of things. And if you think about trying to evaluate this, you would have a hard time finding an antiderivative to the function e to the minus x squared. In fact, they've proven that it's impossible to find an antiderivative of that in terms of elementary functions. You would normally need to resort to a power series, and then that's not really in closed form, right? So you would often just approximate that with a large number of terms, or even a small number of terms. It converges pretty quickly. But to have something exact is often nice. Okay, so here's what we're going to do. This is a little bit tricky. All right. Now I'm going to show you one way to do this, and there is another way, which is perhaps a little bit more rigorous. In the course notes, chapter 14, question 30, has a different way. It's a problem, right? But it has parts, and it sort of walks you through which steps you can do. So that's a different way of approaching it. But I believe it was Professor Walchuk had suggested this way of doing it, which is kind of nice. So here's what we do, is we start by letting this integral equal I. And first of all, how do we even know that converges? Well, Math 138, the comparison test, e to the minus x squared is certainly less than e to the minus x, at least after a certain point, I guess, for x greater than 1, at least. And there's no problems between 0 and 1, so what we're really worried about is, as you go to infinity, is this thing going to converge? But it's less than e to the minus x, which you could easily work out the integral to, and so by the comparison test, this one's also convergent. So what we're going to do is we're going to let that, whatever number that equals, be I. So I equals the integral 0 to infinity e to the minus x squared dx. Alrighty, and so then what we're going to do is say that, well, let's multiply both sides by I and see that I squared equals I times the integral from 0 to infinity e to the minus x squared dx, right? I've just multiplied both sides of the equation by I. Okay, so, well, first of all, remember this variable x. That's just a dummy variable. We could change that to any letter we want, and it would still give you the same value, right? Because you're sort of plugging in the endpoints. And of course, you'll see me today write infinity when really what I mean is some number, say capital R, right? And then with the limit as R approaches infinity in front of it. So I'm going to be a little bit sloppy that way to save space and time by just putting the infinity in the upper endpoint. Now, so the I could also be written as the integral from 0 to infinity of e to the minus y squared dy. Okay, and then we're still multiplying by the integral 0 to infinity of e to the minus x squared dx. Okay, oops, pardon me, dx. Alrighty, and so, yeah, let's get rid of this smudge there. That's better. All right, and so we have, it's starting to maybe look like a double integral here. So let's think carefully about what we're doing. Now the I, of course, is just a number. So what I could have actually done is I could have thought of bringing this I, which is just a number, inside that integral. So I could have done that in the previous step. And then I would end up with, so I've got I squared still. Okay, and so then I would have ended up, if I brought that entire integral inside here, again, it's just a number, is the integral from 0 to infinity of a bunch of stuff dx. Okay, and that stuff is going to be the integral from 0 to infinity e to the minus y squared dy, okay, multiplied by the e to the minus x squared dx. Okay, and I could also think, okay, well, this is an integral with respect to y. All right, so I'm adding everything up, limit of a Riemann sum with respect to the y variable. So this x here is independent of that y. So I'm going to take this e to the minus x squared and bring it inside that integral. We're used to bringing constants out of integrals, but here we're bringing constants into the integrals. And so what I end up getting is something that looks like a iterated double integral. I get integral 0 to infinity of the integral 0 to infinity of e to the minus x squared times e to the minus y squared, which of course is e to the minus x squared plus y squared. Okay, and that's an integral with respect to y, and then the outer integral is with respect to x. Okay, so this is looking like a double integral, okay, over the region where x goes from 0 to infinity and y goes from 0 to infinity. All right, so what's this region look like? Well, it's just the first quadrant of the xy plane. Right, it's the entire first quadrant of the xy plane. So we've got 0 less than or equal to x less than infinity, and 0 less than or equal to y less than infinity. Okay, again, the rigorous way is to let x go from 0 to, say, capital X, y go from 0 to capital Y, say, and then take the limit as capital X approaches infinity, and the limit as capital Y approaches infinity. And if you think really rigorously about this, if you think of interchanging limits, all right, that you're not always allowed to do that. So, again, I suggest looking at also the more rigorous solution to this. We'll also discuss things like uniform convergence in Calculus 4, and you'll learn more about the intricacies of these in upper year analysis courses or the advanced versions of these calculus courses. But anyway, for now, let's not worry about the infinity. So this region, this looks like a double integral over the entire first quadrant of the xy plane. And so the trick here, to get around not being able to integrate e to the minus x squared or e to the minus y squared, we're going to switch to polar coordinates. The idea being that x squared plus y squared is r squared in polar coordinates, but you get this Jacobian which is equal to r, if you remember, in Jacobian coordinates, in polar coordinates. So if you have e to the minus r squared times r, that's something you can find the antiderivative of. So that's the reason we brought it to a double integral. Okay, so polar coordinates. Okay, you remember what those are. X equals r cos theta and y equals r sine theta. And so you're going to have x squared plus y squared equals r squared. And the region, you can just tell by inspection of the diagram, is your region is theta would go from 0 up to pi over 2. And the r for each theta would go from 0, the origin, all the way out to infinity. Okay. So r is between 0 and infinity, and theta is from 0 up to pi by 2. All right, and we've calculated the Jacobian before for polar coordinates. That's a well-known Jacobian. So we could use the change of variable theorem to get the following. This whole thing, remember, was equal to I squared. So let me just start with saying that equals I squared. All right, and so that's going to be the double integral over the r theta region, which is r going from 0 to infinity, okay, and theta going from 0 to pi by 2. And e to the minus x squared plus y squared becomes e to the minus r squared. We multiply by the absolute value of the Jacobian, and we're going to have an integral with respect to r and theta. So the Jacobian would have had to have been di xy by di r theta. All right, and again, we've calculated this earlier. That thing just equals r. Okay, and if you don't remember that, do it as an exercise. Remember, your mapping is x equals r cos theta, y equals r sine theta, so that lets you directly calculate this Jacobian from the determinant of the derivative matrix. Okay, so exercise. All right, so then you just get the integral of r, e to the minus r squared, dr d theta. So you could work that out. So that'll be the integral. Let's do the theta on the outside. So theta is from 0 to pi by 2, and r goes from 0 to infinity of r e to the minus r squared dr, and then d theta. But of course, this integral here, which is convergent, is of course just a number, so you can take that integral out, and then you'd be left with integral 0 to pi by 2 d theta, okay, which of course is just pi over 2. So what you end up getting is pi over 2 multiplied by, and the antiderivative of that one is what? E to the minus r squared? Well, what's the derivative of that? Minus 2r. We don't have a minus 2, so let's do a minus 1/2 out in front. So the derivative of that one is indeed that one, so that's good. And we evaluate that from 0 to infinity. Again, what I mean by that, right, is we evaluate it from 0 up to, say, capital R, and then we take the limit as capital R approaches infinity. Alrighty, so when you do that, when you let that r approach infinity, that of course would be 0 minus negative 1/2 e to the 0, which is 1. So 0 minus negative 1/2 would give you pi over 4. Okay, so we've got that the I squared must equal pi over 4, which of course means that the I equals the square root of that. Okay, so I, which by the way, as a reminder, is the integral from 0 to infinity of e to the minus x squared dx equals root pi by 2. Again, that was because we calculated I squared, right? I squared is pi over 4. Therefore, I is root pi over 2. Isn't that fancy? So we've calculated this seemingly impossible looking integral exactly without finding the antiderivative of e to the minus x squared. Okay, so just a few comments about this one. So I already mentioned the comment about it being improper, and when you interchange the order of integration, especially with improper integrals, you have to be really careful about convergence. The other comment is you might not have noticed, I didn't check the condition on the change of variable theorem, which not only requires the functions to be nice, sort of continuity-wise, which is fine, but the Jacobian is supposed to be non-zero, right? You're supposed to have an invertible mapping, which would mean the Jacobian has to be non-zero. Or actually, sorry, it doesn't mean that. But anyway, we usually assume the Jacobian's non-zero. And in this case, my Jacobian was r, and so that equals 0 at the origin, and that's sort of the corner of our xy first quadrant in the xy plane. So there's one point for which there's a problem, and we already know with polar coordinates that it's not invertible at the origin, right? For r equals 0, any value of theta will give you the same point in the xy plane, right? 0 cos theta, comma, 0 sine theta. That would always give you the origin. So there is a problem with the invertibility of polar coordinates at the origin. But when you're talking about a region, so again, our region here in the xy plane was that, okay. It turns out when you're talking about one point or even a finite number of points in a region, that's not going to affect the value of the double integral unless the value of the function shoots off to infinity or something there. So if the value of the function, remember I'm thinking of e to the minus x squared plus y squared, the function we had in the double integral. The value of that function is very well behaved here. So if you throw away 1 point, you're not really throwing away any area elements. Remember the idea of a double integral is you slice this up into a bunch of area elements, and you take the value of the function multiplied by the area of the sort of the nearest rectangle to that point. And again, we're going to let these things shrink to infinitely small rectangles. So it turns out even a finite number of points will not affect the value, again, unless the integral was improper in the sense of the function blowing up to infinity at that point, like 1 over x squared plus y squared or something like that. Then you would need to worry about that 1 point missing. But in this case, we don't need to. All right, and a final comment is the error function. So that's a function which is used in many applications. It's called erf of x, or the error function. It even came up in the airflow over in airfoil in fluid mechanics research. But it's also very widely used in statistics. Anyway, lots of areas. So it equals 2 over root pi integral from 0 to x of e to the minus t squared dt. And it's usually expressed as a power series. But notice that if we allow x to approach infinity in this function, we get 2 over root pi integral 0 to infinity of e to the minus t squared dt. Of course, t is just a dummy variable. That integral was root pi over 2, which gives this whole thing a value of 1. And so we say that that function has been normalized so that as x approaches infinity, the value approaches 1. So that this thing here is just a normalization factor, and now you know where it comes from. And that's all I've got. Have a great day.